Hi everyone, my name is Ramin Hassani from Vienna University of Technology. Today, together with my colleague Matthias Lechner from the Institute of Science and Technology Austria, we will present our paper entitled Gershgorin Loss Stabilizes the Recurrent Neural Network Compartment of an End-to-End Robot Learning Scheme. Neural networks with continuous time hidden states have recently received increasing amount of attention within the machine learning community. This is due to their several benefits, such as adaptive computations by using different numerical solvers, parameter and computational efficiency, and their strong ability to model time series. A neural network F with various architectures can be built to give rise to a set of expressive dynamical systems. A more stable variant of time-continuous networks is the CT-RNN. One can observe the difference, which is just a recurrent term, which helps the stability of the model to bring back its state to equilibrium with a time constant tau. CT-RNNs are universal approximators with high degrees of nonlinearity. Their dynamics become more and more complex and uncomprehendable as the size of their networks grow. But do we need such degrees of complexity for real-life applications? Let us investigate this by linearizing a CT-RNN network and unrolling it by means of an explicit Euler ODE solver to form a linear dynamical system, LDS, as a recurrent neural network instead.
So in this paper, we want to design a linear dynamical system-based recurrent neural network. So in this regard, we design a new regularization scheme to ensure the stability of the linear dynamical system because of the following considerations. So in a nonlinear recurrent neural network, for example, LSTM, we can just ensure the stability of the system by applying a clipping. However, on a linear dynamical system, we cannot do this because it would destroy the linearity of the system. So instead, we have to ensure the stability by other means because we don't want to have assumptions on the inputs. Because first of all, they may not be available always. Second, because we want to apply nonlinear transformations to the input by means of fully connected and convolutional layers. And finally, we don't want to destroy the expressivity and generalization ability of our models. So as a result, our loss or regularization scheme only ensures the stability of the autonomous system, but not the closed loop system. Our goal is to perform end-to-end robotic learning. Here we have given a linear dynamical system. And we, as I just said, we assume it's autonomous. So the input U is assumed to be 0. And when we look at an autonomous dynamical system, we know that we can look at the eigenvalues to know if the system is stable or not. We want to basically optimize the eigenvalues, but we cannot do that directly because they depend on the eigenvalue decomposition. So instead, our idea is to use the Gershgorin circle loss as a surrogate loss of moving the eigenvalues of the system. And this is, our loss is based on the Gershgorin circle theorem, which is basically a bound on the eigenvalues by looking at the diagonal plus these R values, which are the sum of the absolute values of the row of the matrix. So basically, if the system is non-stable and has positive eigenvalues, we can just optimize the Gershgorin circle loss, and it will ensure that at some point the system becomes stable. So here we have our training algorithm. Given the inputs, we first initialize the parameters of our system by making sure that the autonomous system is stable. By basically, as long as the eigenvalues that have a non-negative real part, we optimize our Gershgorin loss. Then in the training loop, we perform a normal gradient descent step on the training loss. And then, similar as before, as long as we have non-negative real eigenvalues, we optimize our Gershgorin loss. And finally, we log the validation loss throughout the training and store the best configuration so that we can have at the end of the algorithm, return the parameter configuration that performs best on the validation set.
Our algorithm allows us to design end-to-end neural network instances which perceive the observation variables either by multi-layer perceptrons or convolutional layers, and are consist of a linear recurrent neural network. This linear module is regularized by the Gershgorin loss compartment. It is worth noting that a rich set of prior work on learning a stable dynamical system has been proposed. This includes the work on Lyapunov-based methods, approaches on contraction theory, and similar schemes to ours, but with a fixed basis function. The primary distinction of our work to that of these prior works is to enable end-to-end learning of a stable dynamical systems as recurrent neural network instance stacked with a nonlinear module. This enables us to compare our results with other RNNs deployed for modeling dynamical systems. To evaluate our method, we designed two experimental settings within the context of learning from demonstration. First, we looked into imitation learning tasks in the half-cheetah environment, which translates 17 observational variables to 6 control signals. For this rather straightforward task, we designed our learning system with MLP dense layers stacked to our LDS-based RNN to perform an imitation of the cheetahs running. In the second task, we designed an obstacle avoidance real-life environment for our Pioneer mobile robot. We collected training data from episodes of collision avoidance experiments in a lab environment with a couple of objects. The observation space in this environment is the 540 LiDAR channels. We designed 4 convolutional layers to perceive the LiDAR inputs and concatenated them with a robot's pose estimation input and fed them to our recurrent neural network instance. These experiments also enabled us to compare our results to that of related works on end-to-end learning from demonstration. Here we see the results of the half-cheetah imitation learning experience. The nonlinear models such as LSTM and CTRNNs show a better performance during learning. However, the maximum return for the LDS networks was superior on the average of 10 runs in practice and in actual testing. This was true also for the obstacle avoidance environment, where the results were also interesting. We observed that all tested networks, even an unconstrained LDS, can learn the task. But when we tested them in real life in the closed loop environment, we witnessed that the unconstrained model failed to avoid collisions. Let's watch the performance of these learned networks on an unseen test set in practice.
Okay, here we have a video of the LSTM performing the obstacle avoidance on a scenario that is not present in the training set. And as we see, the LSTM can avoid the first obstacle, the box, but it crashes then into this chair, as we see. So basically the LSTM fails on this scenario. Here we see the continuous time recurrent neural network, which is also capable of avoiding the first obstacle. However, similar to the LSTM, it will crash, as we just will see, into the chair here. Next, we have our linear dynamical system, but without our loss optimizing. And we'll see that it crashes even in the first obstacle. So it fails to avoid even the first obstacle. And finally, we have our linear dynamical system trained with our Gershgorin circle loss to ensure the stability of the autonomous system. And we will see that it's the only tested agent that can safely maneuver the Pioneer robot through all obstacles without any crash. So in summary, we propose a new regularization loss for learning linear dynamical systems. And we introduce an end-to-end learning algorithm to stack this stable linear dynamical system with non-linear deep learning layers. We evaluated our approach on a simulated and real-life robotics experiments and compared the performance to modern non-linear RNN. Thank you for listening. If you have questions, feel free to contact us or check out the code repository on GitHub. Thank you.
Thank you.